Welcome viewers, in this video we will see the details about substitution theorem. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. Substitution theorem, one of the theorem available in the circuit theory. First we will see the statement. Any branch of network can be replaced by a different branch as long as its potential and current remain unchanged. So in any network, we can change the branch from one branch to another branch, but the potential and current should be remain unchanged. Without affecting potential and current, we can replace a different branch. When the original branch is passive, either a voltage source or current source is generally used for substituted branch. So it should be passive. The original branch is passive, then either voltage source or current source can be substituted. This principle is sometimes useful in analyzing the behavior of the network. So the application is we can analyze the behavior of the network. Since the solution must be known before substitution can be done, this principle is useless in finding numerical solutions. So only we can analyze the network. Numerical solutions not available. Right? So since the solution must be known before the substitution, so we should know what is the voltage and current. Thereafter only we are replacing, we are substituting. So that is given. So the numerical problems we cannot see that. We can analyze the network. So the network can be replaced by different branch without affecting current and voltage is nothing but a substitution theorem. Now we'll see the example. So consider the network shown below. We will see the network is available. It's a 48 voltage is there, right? There are 1, 2, 3, 4 resistors available. 4 ohm, 2 ohm, 8 ohm and 6 ohm. The 6 ohm is taken as a load terminal, or the terminal is marked as PQ, P and Q, right? The 48 voltage is available. The 6 ampere is flowing through this 4 ohm resistor. Thereafter in the second loop, this is maybe the first loop, second loop, 3 ampere is flowing in this second loop. So 3 ampere is flowing through the 6 ohm resistor. Now we are going to replace the branch, so that we are going to substitute here between the terminal P and Q. The 6 ohm available and 3 ampere is flowing. So what is the current through this branch? IPQ. Current flowing through PQ is 3 ampere. What is the voltage? VPQ is nothing but V equal to I into R. I is 3 ampere, R is 6 ohm. So 6 into 3, 18 voltage. Right? So we are going to substitute this branch PQ with a different voltage source or current source. For that we need to maintain the current flowing through PQ is 3 ampere. We need to maintain the 3 ampere. Similarly, the potential across P and Q, VPQ is nothing but that is the voltage across 6 ohm resistor is 6 into 3, 18 voltage, right? So now we'll see what are the possibilities to replace. We substitute this terminal PQ with the different branches with the value of current equal to 3 ampere and voltage equal to 18 voltage, right? Now we'll see the all the possibilities. What are the possibilities are available? So the branch PQ has current of 3 ampere and voltage 18 voltage. Without changing these two values, we can replace the branch PQ by any one of the branches shown below. So there are 4 possibilities available. This PQ, the terminal PQ, we are going to change. That is 6 ohm, 3 ampere. This is the original. Already 6 ohm is available with 3 ampere is flowing. So current is 3 ampere, voltage is 3 into 6, 18 voltage. So directly we can replace with 18 voltage source, right? So the 18 voltage source, so see that the current also 3 ampere. And another possibility is we can change with 12 voltage in series with one more resistor, 2 ohm. The 3 ampere is flowing. So what will happen? This 12 voltage is available. Already current is maintained 3 ampere. So 3 into 2, the voltage drop across this resistor is 3 into 2, 6. So 6 plus 2, 12, 18 voltage. So we can maintain the 18 voltage. Here 18 voltage source is directly connected. Here 12 voltage source is connected, but we have one 2 ohm resistor available. The voltage drop across 2 ohm resistor is 2 into 3, 6. So 6 plus 12, totally 18 voltage will be there. And another possibility is the voltage source is connected in reverse. This terminal is negative and this terminal is positive. Here plus minus minus plus. So we will get the negative voltage here. That is 9 voltage. In series with we have 9 ohm resistor available. The current is maintained as 3 ampere. So what will happen? Here minus 9 voltage is available. This will be plus 12 voltage. The terminals are reversed. So we have minus 9 voltage. What is the voltage drop across this 9 ohm? 9 into 3, 18. 9 into 3, 27 voltage. Plus 27 voltage will be there. 27 minus 9. From 27 we need to subtract minus 9. So that we will get the 18 voltage. The 18 voltage will be maintained in this branch PQ. Right? So in the first possibility, 18 voltage source is directly connected. In second possibility, 12 voltage source connected in series with the 2 ohm resistor. So 2 into 3, 6 voltage plus 12, 18 voltage is maintained. In the third possibility, 9 voltage source is connected in reverse order. So that we got minus 9 voltage. But we have one 9 ohm resistor is available. So 9 into 3, 27. 27 minus 9 we will get 18 voltage. So on all the cases we are getting 18 voltage, right? So the original branch PQ with 6 ohm resistor and 3 ampere, that is a voltage drop of 18 voltage is replaced with these 3 different possibilities. Now we will go for the further description. The substitution theorem can be stated in the following simplest way. Another one more way of statement is available. A branch of a network carrying a current I can be replaced by a voltage of value I into Z. V equal to I into R. I into Z, impedance, current into impedance. Where Z is its branch impedance without affecting the other parts of the network. Right? So the branch of network carrying current I. In that we are going to replace with a voltage. Replace by a voltage. That voltage value is I into Z. The I is already available. Current is flowing. What is current is flowing? Into Z is nothing but impedance of that network. So that if we replace the voltage with I into Z, that will not affect the other part of the network. So this is the another way of the statement. Now we'll see the compensation theorem. So that is the corollary of the substitution theorem. The compensation theorem, it is the corollary of substitution theorem. Right? Both are interrelated. So we'll see the statement. When the resistance R or impedance, in case of AC network, impedance of a branch carrying current is increased to R plus dr. Dr is the change in resistance. Otherwise, Z plus dz. Dz is change in impedance. The changes takes place can be found by connecting series voltage I into dr or I into dz, opposing the current flowing in the branch Z plus ds. Right? So one network is available with resistor R or impedance. In that we can increase, in that the current is increased to, the carrying current is increased by changing the resistor R plus dr or Z plus dr. The changes takes place can be found by connecting series voltage source. When the resistor is increased, we have to connect the series voltage. That voltage is I into dr or I into dz, so that we can compensate. While increasing the resistor or impedance, the corresponding series voltage should be added. Right? That voltage is nothing but I into dr, change in resistance, or I into dz, change in impedance, opposing the current flowing in the branch of impedance Z plus dz. This voltage is called a compensated voltage. That is given by I into dr or I into dz. So it is very simple. In previous substitution theorem, the branch is replaced by all other combination. Voltage source or current source is replaced by maintaining the current and voltage. Here we are adding the resistor so that the compensated voltage is connected. That is calculated as I into dr, current into change in resistance. This is the original current flowing in the circuit. After increase the resistor, that is multiply with I, that is nothing but Vc. So while increasing the resistor or impedance, we need to connect the compensated voltage, that is calculated as I into dr or I into dz. Vc is a dependent source. The polarity of Vc must be to oppose the original current. The polarity must be opposing. You have to connect in reverse order, right? So this is corollary of the substitution theorem. We will see the further important points. The compensation theorem is used to study the changes in the voltage and current of a circuit when the impedance of any one of the branch is changed, right? So the compensation theorem mainly used for changes in voltage while changing the impedance. So that is called R plus RR. When the resistor is increased from R to dr, what is the changes in the voltage? How the voltage and current will affect? The change in current and voltage in each branch of circuit is the current or voltage that would be produced by the opposing voltage. It's called a opposing voltage. That's why we are connecting the compensated voltage in opposing, in a reverse order, opposing order, right? So the thing is, while increasing resistor or impedance, there is a change in voltage or current, that is nothing but opposing voltage. While changing the resistor, one opposing voltage is created. So that is called a compensated voltage. So that we should connect in a reverse order. So in this video we discuss about the substitution theorem and corollary of substitution theorem, compensation theorem. How to change the, what will happen if the resistor is increased, that is compensated by compensation voltage. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we will see the solved problem based on the substitution theorem. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. Solved problem for substitution theorem. For the network shown below, substitute the branch AB by voltage source or current source. We know that substitution theorem means the any branch can be replaced by some other branch by maintaining voltage and current. We can replace with other elements, but we should maintain the current and voltage. For example, consider this, the network. The 12 voltage source is available. 1, 2, 3, 4 resistors are available. 2 ohm, 2 ohm, 4 ohm and 2 ohm. Here we are going to substitute. It is termed as the terminal AB. So we need to replace this terminal, this branch, by a voltage source and current source, provided the current flowing through this branch AB and voltage across this branch AB should be maintained. So we need to find what is the current flowing through AB, what is the potential across AB. Accordingly, we can replace with voltage source and current source. The original current and voltage should be maintained across AB. Thereby we can replace by voltage source and current source. So first we will find the what is the current and voltage available across AB, right? So in order to find the current, we need to simplify this resistor. So from this diagram it is clear that these two are connected in series. These 2 ohm and 2 ohm are connected in series. That is parallel with this 4 ohm. And that is connected in series with this 2 ohm, right? So this 2 ohm and 2 ohm are connected in series in parallel with 4 ohm. First we will simplify this network. So 2 plus 2, 4. That 4 ohm is connected in parallel with this 4 ohm. So the equivalent resistance is R1 into R2 divided by R1 plus R2. That is R1 is 4 ohm. R2 also 2 plus 2, 4 ohm. 4 into 4 divided by 4 plus 4. 16 divided by 8, 2 ohm. Right? So this branch is 2 ohm. That is connected in series with this another 2 ohm. This resultant 2 ohm is connected in series with the 2 ohm. So the final resistor is 2 plus 2, 4 ohm, right? The total resistance of this network is 4 ohm. So from that we can find the total current. Total current IT equal to V by R. V is nothing but 12 voltage. R is nothing but 4 voltage. So 12 by 4 is 3 ampere. So current flowing, the total current available in the circuit is 3 ampere, not a branch AB. The total current available in the entire network with the voltage source 12 voltage is 3 ampere. So IT equal to 3 ampere. Similarly, we need to find what is the voltage across AB. So voltage across AB, V equal to I into R. R is 2 ohm. What is the current? We need to find what is the current flowing through AB, right? So the total current is 3 ampere. The total current available is 3 ampere. So from this voltage source 3 ampere is flowing. At this point the current is diverted. The current is diverted. See this is 4 ohm. This is also 4 ohm. Both are equal resistor. So 3 ampere will be equally divided. 1.5 ampere and 1.5 ampere. If it is different value, we can go with the current division rule. But here the resistor values are equal. 4 ohm and 2 plus 2, 4 ohm. So the equal amount of current will be divided. So IAB is nothing but 3 divided by 2, 1.5 ampere. So VAB equal to I into R. I is 1.5 ampere. The resistor is 2 ohm. So 3 voltage, right? So the current through the branch AB is 1.5 ampere. Voltage across AB is 3 voltage. So by maintaining these two values, current and voltage, we can replace with either current source or voltage source. That is the question given, right? Now we are going to replace the branch AB with voltage source, then by current source, by maintaining these two values, 1.5 ampere and 3 voltage, right? Now we'll see how to replace the value. By substitution theorem, the branch AB may be substituted either by independent voltage source of value 3 voltage, that is our requirement, with a branch current of 1.5 ampere. If we replace with voltage source, the voltage value will be 3 voltage and the current flowing through the network is 1.5 ampere. Or by independent current source with the value of 1.5 ampere with the branch resistance, the voltage is 3 voltage, right? So either we can replace with voltage source with 3 voltage and 1.5 ampere, or current source with 1.5 ampere with 3 voltage, right? So these two possibilities we will check with this. So these two cases can shown below. So this is the original network AB. Initially we have 2 ohm resistor, now replaced with voltage source. Here another possibility, we can replace with current source, right? What is the current value? 1.5 ampere. The voltage drop across should be 3 voltage. Here voltage source, what is the voltage source value? 3 voltage. The current flowing through should be 1.5 ampere, right? So modified network with branch AB replaced by the voltage source. Modified network with branch AB replaced by current source, right? So by maintaining current and voltage, we replace the voltage source one possibility, current source another possibility. So in this problem we discuss the substitution theorem. The given network, in this the branch AB is replaced by voltage source and current source. Before that we need to find what is the voltage across AB, what is the current flowing through AB. By using that value, there the branch is replaced by the current source and voltage source with maintaining the required value of current and voltage. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we will see the solved problem based on the compensation theorem contained in the DC circuit. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. We'll see the statement of the problem. Find the current when the resistance of 5 ohm is added in series with the existing 5 ohm using the compensation theorem. So the compensation theorem is nothing but while increasing the resistance value or impedance, there will be opposing voltage and current that is identified by the compensation voltage. That's called compensation voltage Vc. Similarly here we are increasing this 5 ohm resistor to another 5 ohm resistor. While increasing this 5 ohm with another 5 ohm, 5 plus 1 10 ohm, there will be opposing voltage. That is called compensation voltage. We need to identify what is the compensation voltage, right? So in this network, the voltage source is 15 voltage source available and one series resistor 20 ohm is there. Another resistor is 5 ohm. That is marked as terminal AB. In this terminal AB only, we are going to increase the resistor from 5 to another 5 ohm. 5 plus 5, 10 ohm. So first we need to identify what is the current flowing through this circuit, original circuit. Then we'll go to increase this 5 ohm. So while increasing, there is a opposing voltage that is called Vc, compensation voltage, that we need to identify. So first we will find what is the current flowing through this circuit. So this circuit is simplified circuit only one voltage source is available. These two resistors are connected in series. So easily we can find the current value. For the given circuit, the current is I equal to V by R. V is nothing but 15 voltage. R is nothing but 20 plus 5. This is the original circuit. Then only we'll go for increasing the resistance. Now we'll take resistor as 5. So 20 plus 5, 25. 15 by 25, it is 0.6 ampere. This is the original current flowing in the circuit, right? So before going to increase the resistor value, we identify what is the current flowing through the original circuit, that is 0.6 ampere. Now we'll go to the increasing of resistor. So in the step 2, the increase in resistor dr equal to 5 ohm. We are going to increase the resistor to 5 ohm. That is dr means change in resistor 5 ohm. So due to the change in resistor, the compensated voltage, this is a formula, Vc equal to I into dr. What is this I? I is the original current flowing through the circuit. This dr is change in resistor. We are going to change to 5 ohm resistor, right? So the original current what we calculated 0.6 into 5, that is 3 voltage. So we need to go with the compensation voltage of 3 voltage, right? So due to change in resistor, there will be a opposing voltage, that is nothing but called a compensation voltage. That value is 3 voltage. Connecting this source Vc in the branch AB and killing the given source Vs, the following circuit is obtained. So what we need to do, we need to connect this voltage source in series with the branch A. Then we'll remove the original source, that is called killing the given source, means Vs should be removed, right? Now the polarity of Vc are so as to oppose the original current. The polarity should be opposing, so that is called opposing voltage. That's why it's called a compensated voltage, right? So after this modification, we'll see what is the changes in the circuit. See this original source is removed. Compensated voltage is connected, plus minus 3 voltage we already calculated. This resistor is 5 ohm. Additionally, we can added one more 5 ohm. That is the problem is given. 5 ohm is increased to another 5 ohm, right? This is another 20 ohm already available. This I dash, the current is flowing in opposite direction. Why? While changing the voltage, there will be opposing voltage and current that will oppose to the source what is available. That's why the current is flowing in reverse direction. That is a statement of the compensation theorem. The compensated voltage or current is opposing, should be connected in reverse order, right? Now we need to find what is this current I dash. That is because of increasing the resistor, this is the compensated voltage. Due to the compensated voltage, what is the current flowing? We already calculated the current, that is 0.1, 0.6 ampere. Original current is 0.6 ampere. Now we'll see what is the current I dash. So I dash equal to Vc by R, voltage by resistance. Now the voltage is 3 voltage. The resistor is 20 plus 5 plus 5. Another 5 also added. Initially 20 plus 5, now one more resistor, the change in resistor is 5. So 20 plus 5 plus 5, so that 3 divided by 30, that is 0.1 ampere. I dash is 0.1 ampere. The opposing current flowing in the circuit is 0.1 ampere. Right? What is the meaning? The resistor 5, while increasing to another 5 ohm, the 3 voltage source is connected. The compensated voltage is 3 voltage. Due to the increase in resistor, this is the voltage, and this is the current flowing in a opposite direction. Right? So what is the original current now? What is the resultant current? By superimposing the final current flowing in the given circuit with increase in resistor is I minus I dash. I is original current 0.6 minus I dash 0.1 is 0.5 ampere. Right? So initially 0.6 ampere is flowing. Due to increase in voltage, 0.1 ampere is flowing in opposite direction. So 0.6 minus 0.1 is 0.5 ampere. So after increasing the resistor, the current is now changed to 0.5 ampere. So in this problem we discuss about the compensation theorem in the DC circuit. The resistor value is increased. Due to that, there is a opposing voltage. This is called a compensation voltage. First we calculated the original current. From the original current and change in resistor, the compensated voltage is calculated. From the compensation voltage, the opposing current is calculated, I dash. From I and I dash, we calculated the change in what is the current flowing through the circuit. What is the changes in the circuit? I minus I dash. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video, we will see the solved problem based on the compensation theorem contained DC circuit. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. The given problem is, by use of compensation theorem, find the voltage across BD in the bridge circuit shown below in the network A. I will see the network A. So this is the network A is given. So we have it's a balanced bridge. The terminal A, B, C, D. Between B and D, the resistor is connected. And other side also resistor available, the equal amount of value R. So this is the voltage source Vs. Is named as a network A. When the resistor in the branch BC is changed from R to R plus DR. So this is the branch BC. In this we are going to change the resistor from R to DR. The additional resistor is added. Take the Vs equal to 20 voltage. This Vs is 20 voltage. The resistor R value, for all the R value is 10 ohm. The small r is 5 ohm. Change in resistor is 2 ohm. Right? So the bridge circuit is given. In this, the BC, the R value is changed to R plus DR. The Vs value is 20, R value is 10 for all the resistor. Small r is 5 ohm. Change in resistor is 2 ohm. We know that in compensation theorem, when the resistor is added, with R is added with some more resistor, there will be a opposing voltage or current. That is called a compensation voltage. We need to identify the compensation voltage that will oppose the original current. So this is the compensation voltage. So in this branch, the resistor is changed from R plus DR. Due to that, there is a opposing voltage or current that is identified by the voltage source VC. That is called compensation voltage. So now we need to identify what is VC value. What is VC value is I into DR. The change in resistor. Change in resistor is 2 ohm. I is nothing but original current. The current flowing in the network A. Right? So current flowing through the network A, change in current, change in resistor. From that we can identify the compensation voltage. Right? So this network A is the original one. Network B, the resistor value is increased so that the compensation voltage source is connected, and also this voltage source what is available in network is removed. While removing voltage source, it is short circuited. Right? Now the voltage is compensated here. We need to identify what is the compensation voltage, that is given by I into dr. Now we'll see, find the I value, the current flowing through the original network A. What is the current flowing through the original network? From that we can easily identify the current compensation voltage Vc. Right. The step 1, in the bridge circuit shown in network A, the product of resistor in the opposite arm is same. So all the resistor values are same, that is 10 ohm. So it is balanced one. So the bridge is balanced. So the VBD, the small r, what we connected is 0. So that the current in each other resistor is nothing but I equal to V by R. So R plus R, the bridge is balanced. So one arm here R plus R, another side R plus R. So that 2R. So Vs divided by 2R. So Vs is 20 divided by 2 into resistor value is 10. So 20 divided by 10, 20 divided by 20, it is 1 ampere. Right? We will see how it is 2R in this network. So this R value, all R values are equal. So that bridge is balanced. So the resistor, the voltage drop across this is 0. So that these two are become a series connected. These two resistors also series connected. So R plus R, 2R. So by using 2R only we calculated the current I. Right? So this is the 2R. Because of balance become 2R. Now we'll see, now we'll go to the how to find the compensation voltage. Step 2. Now let the additional resistor dr be introduced in the branch BC. As a result, current changes in the various branches. So let us introduce a compensation voltage Vc, that is I into dr, that is equal to 1 into 2. Current what we calculated is 1 ampere. Change in resistor 2 voltage. So the compensation voltage is 2 voltage. Polarities being such that it drives current in a direction opposite to that of I. Right? So it is opposite. Because of change in voltage, one more current is flowing from the compensated voltage source, that is opposing each other. So that we need to connect in such a way that it will oppose the original current I. Now we'll see how it is connected. Now the compensated voltage is introduced in the network B. Vs is short circuited, that is the rule. While connecting the additional resistor, we need to connect the compensated voltage by removing other sources. While removing voltage source, it is short circuited. So from a network B, we can find the changes in the current in various branches due to change in the resistance in BC. Right? So the BC, we added the additional resistor. For that we calculated the compensated voltage. From this we can identify what are the changes in current. The change of current in BC is only asked, so that voltage across BD is required. Right? So no need to find other change in current, only BC is required. The current flowing through BC. So what we need is the voltage across BD is required. Now we'll see the simplified diagram. So from network B, this simplified diagram is drawn. Right? So the terminal B, C and A is short circuited, because between C and A the voltage source is available, that is removed and short circuited. This is terminal D. Between C and D one resistor available, between A and D one resistor available. Similarly between B and C one more resistor available. Now we'll go to the network A so that we are able to understand this circuit. So this is the original network. This is the after compensation, this is connected. So this is BC. So B and C, between we have resistor and change in resistor compensated voltage. This A and C is connected. So A and C is a common terminal, both are same. Right. So within BC, the A also same. So what are the things available? This between B and D one resistor R small is available. Between C and D this resistor R is available. Similarly A and D one more resistor available. So that is given in that diagram. With first we will refer BC. BC we have R plus DR and voltage source. In that we have one more resistor BD. Then between C and D one more resistor. This C and A is same. So between C, A and D also one more resistor is available. Now we'll see that the simplified diagram. Now we are able to understand clearly. First we will refer with BC. Say resistor, change in resistor, compensated voltage. Between B and C, the R is connected. Similarly, between B and D, small r is connected. Right. Between C and D, one resistor. Between A and D, one resistor. Because now C and A become the common point. So see that there are four resistors. R plus D are R. And the resistor available between BD. Right. So this resistor connected between B and C. These two are connected between C and D, A and D. Right. That is clearly given in the diagram. Now that is further simplified here. Now this is the terminal BCA. The terminal BCA. This branch is drawn in a vertical manner. So we have one resistor R is available. This resistor R is available. And this is see that these two are connected in parallel, that is in series with the resistor R. So that R and R both are connected in parallel mean it become half of the value R by 2 and this small r. So this is the terminal D. This terminal D. Right. So A, CA and terminal D. I explain again. This B with the common terminal CA is drawn in the vertical manner. In parallel with that one resistor R is available. On other side these two are connected in parallel, so it become R by 2. This is a D. From D to B we have one more resistor, small resistor R. Right. This is a simplified diagram. Now we can go for further simplification. What is the further simplification? These two are connected in series, that is in parallel with R plus D R. Right. These two are connected in series, then it is parallel, that is parallel with R. Right. Now we'll go for the simplification. So small r plus R by 2 is connected in series, that is parallel with the capital R. This R value is 10, small r is 5, capital R is 10 by 2. So it becomes 5 plus 5. 10 ohm parallel with 5 plus 5, that is 10 ohm parallel with 10. So R1 R2 divided by R1 plus R2. 10 into 10 divided by 10 plus 10. 100 by 20 equal to 5 ohm. Right. So both the resistors are equal mean we will get the half of the value R by 2, what we discussed earlier. Right. Both the resistor values are equal mean half of the value. So finally we have R 10 ohm is parallel with 10 ohm. So we got 5 ohm. Now see this, the circuit is further simplified. Right. Only R1. Compensated voltage R plus DR. All others are resistors are simplified and written as R1. Right. The R1 value is 5 ohm. Now we can find the I1 current, the total current flowing in the circuit after compensated voltage. After compensated voltage we can find. So what is the value? I1 equal to VC divided by R1 plus R plus delta R. The VC is 2 ohm. We already calculated. R1 what we calculated is 5 ohm. Then capital R is 10. Change in resistor is 2. So that is what is available in this circuit. Right. So I1 equal to V divided by R. V is VC. R is R plus DR plus R1. Right. That is given here. So 2 divided by 10 plus 5, 15 plus 2, 17. 2 by 17 ampere. So the current I1 in this nothing but 2 divided by 17 ampere. Now we'll go for further simplification. So now again we'll refer this simplified diagram. So this is the current I1, that is current flowing from the compensated voltage. At this it is splitted to I2. Right. The current flowing through this is I2. What we calculated here is I1. Total current is calculated. But what we need is the current flowing through this resistor R, small r. That is the required, or R by 2. This small r is required. So by using current divider rule, we can find what is the current flowing through this small r. Right. So the total current what we calculated 2 divided by 17. That is this value. At this point it will be splitted. So one branch is R. Another branch is R plus R by 2. So we need to find the current divider rule. What is the current divider rule? The current I1 is nothing but total current multiplied by other branch resistor. This is the other branch. What we need is this I2. So R divided by total resistors, R plus small r plus R by 2, right? So what we calculated is I1 is total current 2 by 17, but here what we need is current flowing through this branch I2, that can be calculated by current divider rule. Current divider rule is total current multiplied by other branch resistor divided by total resistor. So this given. Step 5 is to find the current through small r. So I2 is nothing but total current multiplied by other branch R divided by total resistor R plus small r plus R by 2, what we discussed in the diagram. So the current, total current what we calculated 2 by 17. R value is 10 divided by this R value also 10, small r is 5, 10 by 2 is 5. So that 2 divided by 17, 10 divided by 10 plus 5 plus 5, 20. Right, 2 divided by 17 into 10 divided by 20. After simplification we got 1 divided by 17. The current flowing through the branch BD is 1 divided by 17. From that we can find the compensated from the change in voltage. From that we can find change in voltage. So voltage across BD is R into I2. R value is 5, I2 what we calculated 1 by 17. That is 5 by 17. So that simplified is 0.29 voltage. So due to change in resistor, that is we added with 2 ohm, for that there is a compensated voltage is calculated, opposing voltage, right? From that opposing voltage we calculated I1 and I2. From that we calculated what is the voltage across BD. Change in voltage is 0.29 voltage. Due to additional resistor, the voltage in the branch is BD is 0.29. So in this problem we discuss how the compensation theorem, how when the resistor is added, what will happen, that we need to find the compensated voltage. From using that we can find change in voltage in that particular branch. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we will see the solved problem based on the compensation theorem with the AC circuit. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. Now we'll see the problem. In the network shown in diagram A, 50 voltage 40 degree source contain a current I. The 10 ohm resistor is changed to 5 ohm. Use the compensation theorem to find the VC and DI as shown in the diagram B. So this is the network A. Contain the voltage source 50 voltage with angle 40 degree. Here one 10 ohm resistor available, one inductor J3 and one capacitor minus J6. In this 10 ohm resistor is changed to 5 ohm resistor. So due to that the current I in the network A is changed to delta I. So in compensation theorem is nothing but when the resistor is changed or added or modified with some other value, there is a opposing voltage or current will be produced in the circuit. That is given by the compensation voltage. So the current in the compensation voltage will be opposing. This is a normal current direction. This is the current direction by the compensation voltage. So while changing the resistor or impedance, there will be opposing voltage and current that is given by the compensation voltage VC. So in the compensation theorem we need to find compensation voltage VC, that is I into delta R. I is nothing but current in the original circuit. Delta R is nothing but change in resistor, right? So our aim is to find VC, that is equal to current in the original circuit and change in current. Here one more question is asked, delta I. The change in current also we need to find. So this is the original circuit A, this is the compensated circuit. So this original voltage source is removed. The voltage source means short circuited. For that we added compensation voltage and 10 ohm is changed to 5 ohm, right? So this is network A and network B. So first we will find the current through this circuit. So that we can find VC. VC equal to I into delta R. Delta R we know that 5 ohm, 10 ohm to 5 ohm. So change in resistor is 5 ohm. The current we need this value. So the current I equal to V by R, voltage divided by impedance of the circuit. After that we need to find the impedance of this circuit also. So how to find the impedance? By seeing the diagram, these two are connected in parallel, that is in series with the 10 ohm resistor. Similarly in the network B, these two are connected in parallel, that is in series with the 5 ohm resistor, because 10 ohm is now changed to 5 ohm. So that is the only difference. Both are very similar. Here 10 ohm, here 5 ohm. These two are parallel in series with the 10 ohm. Here these two are parallel in series with the 5 ohm. Right. Now we'll see the total impedance of the circuit. So the total impedance connected to the source is this J3 inductor minus J6. Both are connected in parallel. Right. So R1 into R2 divided by R1 plus R2. That is the formula for while connecting in parallel. So J3 into minus J6 divided by J3 minus J6 plus 10. This parallel combination is connected with the 10 ohm resistor. Now we'll go to the further simplification. So 10 plus J square minus J square into 18 divided by minus J3. After simplification we got. We know that J square value is minus 1 divided by 18 into 18 divided by J3. Right. So 10 minus, so here minus of minus become plus. So 18 divided by J3. This minus due to that this minus, there we have negative. 10 minus 18 divided by J3. Right. So you can simplify this. 18 3 times 3. 18 by 3 is nothing but it will go the 6 times. So 6 divided by J. In order to remove this J available in the denominator. So in order to simplify, we can multiply and divide by J. So that we can bring this J in the numerator. So what happens? 6, 10 minus 6 into J divided by J square. Again J square is available. The J square value we know that it is minus 1. J square is minus 1. So this minus and minus become plus. So 10 plus 6J. The impedance, total impedance is 10 plus 6J. This is in rectangular form. It's been converted into polar form. For division and multiplication we need polar form. For addition and subtraction we can use this rectangular form. How to convert rectangular to polar? This is magnitude and this is angle. The magnitude is nothing but square root of 10 square plus 6 square. Real term square plus imaginary term square. Then we will take the square root. That is the formula. Square root of 10 square plus 6 square. Real term 10, imaginary term 6. So that is 11.66. The magnitude is 11.66. How to find the angle? Tan inverse B by A. Imaginary term divided by real term. Imaginary term is 6, real term is 10. Tan inverse 6 by 10. So this value is 31 degree. Right? So 11.66 with an angle of 31 degree. The impedance, the total impedance in the circuit. From that we can find the current as well as change in current. So current I equal to V by Z. V is 50 voltage with an angle 40. The current we calculated 11.66 into with an angle of 31 degree. Right. How to find this? You have to divide this 50 divided by 11.66. So that 4.29. Angle divided means you have to subtract 40 minus 31 is 9 degree. Multiplication means the angles are added. Division means angles are subtracted. So this is the current in the original circuit. Magnitude 4.29, angle 9 degree. Now what is the change in resistor? 10 minus 5. 10 ohm converted it is changed to 5. So 10 minus 5, 5 ohm decreases. There is a decrease in resistor. So from that we can find the compensated voltage. I into dr. Current in the original circuit into change in resistor. 4.29 with an angle 9. This is the current. Into change in resistor 5. Right. So that VC equal to 21.45 with an angle of 9 degree. This is the compensated voltage. So we calculated the compensated voltage. One more parameter is asked. We need to find the change in current. Change in current. Right. change in current, how to find? You have to refer the second diagram. That is 10 ohm is changed to 5 ohm resistor. We already discussed. So this inductor and capacitors are connected in parallel, that is connected with 5 ohm resistor. In original circuit there will be 10 ohm resistor. Now it is changed to 5 ohm resistor. So the same thing what we discussed here. Only here 5 plus J6. Previous case 10 plus J6. Right. So that this is the rectangular form. Let's convert it into polar form. How to that? 5 square plus 6 square. Square root of 5 square plus 6 square. So 7.81. The angle is tan inverse B by A. Imaginary term divided by real term. 6 by 5. 50.2 degree. So the magnitude is 7.81, angle 50.2 ohm. So from that we can find the change in current. I equal to V by R. V is 21.45 with 9 degree. This is a compensated voltage. In the network B, we have compensated voltage divided by the impedance what we calculated. By changing the resistor 5, this is the new impedance. 7.81 with an angle 50.2. So you have to divide these two. 21.45 divided by 7.81. So 2.746. Angle how to do? 9 minus 50.2. So that minus 41.2 degree. From 9 we have to subtract 50.2. So this is the change in current. Right, now we calculated the compensated voltage as well as change in current. So in this problem, by using compensation theorem, while changing the resistor value, there will be a opposing current or voltage that can be identified by the compensation voltage. By finding compensation voltage, we can able to identify opposing current. In this problem, we calculated compensated voltage as well as change in current. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video, we will see the solved problem based on the compensation theorem contained AC circuit. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we will go to the problem. In the network shown in diagram A, the 5 ohm resistor is changed to 8 ohm resistor. Determine the change in current through 3 plus J4 ohm impedance. So this is the two networks available. Network A, network B. This is the original network. 10 voltage with 0 degree voltage source is available. 5 ohm and one inductor J5 ohm and one more resistor and inductors are connected in series. 3 ohm and J4 ohm. The problem is this 5 ohm is now changed to 8 ohm. So in the compensation theorem, if the change is any change in the resistor value, what will happen? There is a opposing voltage or current will be produced. That can be identified by compensation voltage VC. This VC will give the opposing voltage or current. See the current direction, it is opposing. Right? So while changing the resistor value, we need to identify what is the opposing voltage given, that is given by compensation voltage. Then how to find this compensation voltage? V equal to I into R. I is nothing but the current flowing in the original circuit. The R is nothing but delta R, change in resistor. 5 ohm changed to 8 ohm. So 8 minus 5, 3 ohm. The change in resistor is 3 ohm. Right? So this is the original circuit. The resistor is changed. Due to that, there is opposing voltage that is given by compensation voltage VC. This VC can be calculated as I into delta R. I is nothing but current in the original circuit. R is delta R is nothing but change in resistor. So first step we need to find what is the current in the original circuit, so that we can find VC. And one more question is asked, current through the 3 plus J4 ohm. Right? So first we will find the current. From that we will find VC. From that we can find the resistor current flowing through this 3 plus J4 ohm resistor. Right? What is the current flowing through this network A? I equal to V by R. Right? R, what is the R value? These two are connected in series. This 3 resistor and inductor. That is parallel with this J5 ohm inductor. That is series with this 5 ohm resistor. Right? So 5 plus J5 into 3 plus J4. Right? So these two are connected in parallel. In this, these two are connected in series. So while referring the network B, See this, while network B, the original source is removed. We have to remove the original source. If it is voltage source, short circuited. Current source means open circuited. Then we have to add the compensated voltage where the resistor is changed. There we have to add the compensation voltage. Right. What is the impedance in this network? It's very similar. These two are connected in series. That is in parallel with J5 ohm. That is series with the 8 ohm. Here 5 ohm. Here 8 ohm. That is the only change. 5 ohm is changed to 8 ohm. This combination is remain same. Right. So now we'll first find the network A. We will find what is the current, what is the total impedance in that circuit. So the total impedance connected to the source referring A, we already discussed 5 plus this inductor and capacitor, this resistor and inductor connected in series, that is parallel with the one more inductor. R1 into R2 divided by R1 plus R2. R1 is J5 inductor. R2 is resistor plus inductor, J plus 3 plus J4 divided by R1 plus R2. So 5 plus J5 into 3 plus J4, we can add this 3 plus this J4 and J5 and J4 can be added, the J9. Right. Now we have to convert this polar form. This is the rectangular form, should be converted into polar form. For addition, rectangular form is easier. For multiplication and division, the polar form is needed. So the J5 is nothing but magnitude is 5, every J refers 90 degree. J means 90 degree. J square means 180 degree. Right. Then how to convert this rectangular form 3 plus J4? This is magnitude and angle. Magnitude is nothing but square root of 3 square plus 4 square. Real term square plus imaginary term square. Square root of 3 square plus 4 square is 25. So square root of 25 is 5. Then this angle, tan inverse 4 by 3. Imaginary term divided by real term. Tan inverse 4 by 3 is 53.1 degree. Right. So this rectangular form is converted into polar form by using this formula. Magnitude 5 with an angle of 53.1 degree. Similarly, we can find this 3 plus J9. 3 square plus 9 square. 9.487. Then tan inverse 9 by 3. 9 by 3 71.6 degree. So this rectangular form now converted into polar form. 9.487 with an angle of 71.6 degree. Now we can go for simplification. So in this simplification, so these all are converted into polar form. So we can multiply these two. 5 into 5 divided by 9.487. That is 2.635. These angles are added. Multiplication means 90 plus 51.1. Divided means from that subtract 71.6. That is 90 plus 51.1 minus 71.6. That is 71.5. Right. Now this is 5 plus, now it is available in polar form. For addition we need to convert into rectangular form. How to convert? This formula is available. This is magnitude, this is angle. Magnitude into cos of angle 71.5 plus J into magnitude into sine of angle 71.5. This is a formula. Right. A cos theta plus J A sine theta. That is the value. A is nothing but magnitude. 71.5 is angle. Right. Magnitude into cos of theta plus J into magnitude into sine of theta. Right. So by simplifying we got 0.836 plus J 2.5. Now we can easily add this. We can add these two values. Right. 5 plus 0.836, that is 6.836. Right. Plus J 2.5. So this value is 1.836. So that 5 plus 1.83, 6.836 plus J5. Again this is in rectangular form. Should be converted into polar form. Right. How to convert? The square root of 6.836 plus 2.5 square. Right. We have to take the square root and real and imaginary terms are squared and added. It is 6.349. Angle is calculated as tan inverse B by A. Imaginary term divided by real term. Imaginary term is 2.5, real term 6.837. So angle is 23.2. So the total impedance of a network A is 6.349 with an angle 23.2 degree of impedance ohm. Now we calculated the total impedance. From that we can calculate the current flowing through the circuit, thereby compensation voltage. So the current source current I through the 5 ohm resistor is I equal to V by R. V is 10 voltage with angle 0 degree. The R is impedance, that what we calculated, 6.349 angle 23.2. So 10 divided by 6.49 is 1.575. Angle is here 0 minus 23.2, so that it is minus 23.2. Divided means we have to subtract the angle. So the current value is 1.575 with an angle minus 23.2 degree. From this we can calculate the compensated voltage. So what is the change in resistor? 5 ohm is changed to 8 ohm. So that change in resistor delta IR is nothing but 8 minus 5, 3 ohm. From that we can calculate VC. VC equal to I into delta R, dr. I is nothing but this value, 1.575 with an angle 23.2 degree. Change in resistor 3, right? So we can multiply these two. 4.725 with an angle 23.2 degree. So we calculated one value, compensated voltage. Next we need to find what is the current flowing through the network, the one more network, 3 plus J4 ohm. For that we need to refer the network B. So this dependent voltage source to be connected with R plus DR 8 ohm resistor. What we calculated, compensated voltage is connected in series with 8 ohm resistor. Keeping only this voltage source and remaining original source in the circuit is shown in network B. That is, the original source is removed, only we need to connect the compensated voltage. From this diagram, the changes in various branches due to change in 5 ohm to 8 ohm resistor is calculated. So now referring the diagram B, again we need to calculate the total impedance, because we need to find the current through the 3 plus J4 ohm resistor. So that Z equal to only change here 8 ohm. Initially here 5 ohm is there in previous. Referring the diagram B, it is 8 ohm. Referring diagram A, diagram A is 5 ohm resistor. So this part is remain same. So what we calculated, 8.836 plus J 2.5. So 8 plus 8.36 plus J 2.5. So it is 9.2. This again this rectangular form is converted into polar form, right? So square root of 8.836 square plus 2.5 square, that is 9.2. Tan inverse B by A, 2.5 divided by 8.836 is 15.8 degree, right? So we calculated total impedance 9.2 with an angle 15.8 degree, right? So only this 8 is changed. Previously in the diagram A it is 5. This value is remain same. So from that we can calculate the current, the total current in the circuit. I equal to V by R. V is 4.725 with an angle 23.2. That is the compensated voltage, what we calculated earlier, divided by total impedance of the network B. This is the total impedance of network B. So these two is divided. 4.725 divided by 9.2, that is 0.515. Angle how to calculate, minus 23.2 minus 15.8. You have to subtract these two angles. Already here minus is there. So minus totally it will give 39. You have to minus 23.2 minus 15.8 is minus 39 degree. So we calculated the current also, the total current. Now we need to calculate current through the 3 plus J4 ohm resistor. That how will you calculate this? By the current divider rule. Total current multiplied by other branch impedance divided by total impedance, right? So we need to find 3 plus J4 ohm resistor. One more inductor is available, J5. The current is divided through 3 plus J4 and J5. So that other branch impedance is J5 divided by total impedance. So while simplifying, this is the total current, J5 divided by 3 plus J9. This J5 is nothing but 5 angle 90 degree. J means 90 degree. 3 plus J9 is converted here by using the formula. This is a rectangular to polar form. Square root of 3 square plus 9 square, 9.489. Tan inverse B by A, 9 by 3 is 71.6 degree. Now everything available in polar form. So these two should be multiplied. 0.515 into 5 divided by 9.487. That is 0.271. Then angle is, these two angles should be added. From that you have to subtract. Already here minus is there. So minus 39 plus 90 minus 71.6. So this value is minus 20.6 ampere. Now we calculated the current through the 3 plus J4 ohm resistor. So that we can find one more value. This current flows in 3 plus 4 ohm resistor in diagram B from bottom to top. From bottom to top, opposing, in opposing direction. So the change in current delta I is this value, 0.271 with an angle minus 20.6 degree ampere. So in this problem, we changed the resistor. Due to that, compensation voltage is calculated. Thereby, current flowing through the branch is calculated. That is nothing but the change in current. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening.